Alright, let's take a look at example problem unit C2, page 7. Okay. The speed of an airplane through the air is obtained by use of a static tube that measures the difference between the stagnation and static pressures. Okay. Let's just take a look at video for a moment. Okay, so this is a video. Pitot-static tube which is attached to the fuselage of this airplane. Obviously, center tube measures the total pressure, side port measures the static pressure, then sensing the pressure difference between them is essentially dynamic pressure. And then that dynamic pressure is going to be given here as airspeed indicator. It's usually knots of airspeed. Knots of airspeed. Okay. So let's continue. Rather than indicating this pressure difference, psi or Newton per meter squared directly, the indicator is calibrated in speed. In other words, this pressure measurement needs to be converted into the airspeed, miles per hour or knots. Okay. This is done using the density of, not always standard sea level, but typically, density of standard sea level or some kind of difference value of density. Density of standard sea level, for example. Okay? Therefore, the airspeed displayed, termed the indicator airspeed on the cockpit, is the actual airspeed only at the standard sea level conditions. Okay. If the airplane is flying at an altitude of 20,000 feet and the indicated airspeed is 220 knots, what is the actual airspeed? This is an interesting question. Let's take a look at airspeed from pitot-static. Okay. Now remember, a pitot-static probe measures the pressure difference. Well, let's begin with Bernoulli's. Bernoulli says static pressure plus 1/2 rho v squared dynamic pressure is equal to PT, total pressure. So this is Bernoulli's. Bernoulli's equation. What the pitot-static probe does is it is going to measure delta P. Delta P is PT minus PS. This is what pitot-static measures. Therefore, looking at this original Bernoulli's equation, meaning that PT minus PS, which is delta P, is essentially equal to 1/2 rho v squared. Therefore, you can solve this equation for V. Velocity V, which is called airspeed, is square root delta P divided by rho. So 2 times delta P divided by rho. Very simply derived from Bernoulli's equation. This is the airspeed. Okay. Airspeed determined by combination of pitot-static and then measurement device, some kind of measurement device. Could be U-tube differential manometer or digital pressure transducer or any kind to determine this delta P. This is fine. Delta P can be measured, yes. One thing we can never measure is this: air density. Density is how much mass is packed up by a given unit volume of air. That's called air density. We can never measure such a thing. This is non-measurable quantity. Mass is non-measurable. I think we covered it at the very beginning of the semester. This is a fundamental quantity or property, and then we can never directly measure mass. Density also. Important. There's nowhere on Earth we can measure density of air direct. We can obviously determine density assuming air acting as an ideal gas, applying P equal to rho T. Of course, we can measure pressure, we can measure temperature. Assuming that air is ideal gas, we can determine density out of it. But sometimes we really never know if air is always ideal gas. If it's not ideal gas, this is only just a guesstimate. Okay? So a problem is this density. Usually airplane has no capability to determine air density. So what do? We are going to assume the density. So give some kind of density value, then airplane determine the speed. So let me introduce you two different kinds of airspeed. One is true airspeed. Which is, you can never get it. This is theory, okay? This is only theoretical. You can never, in reality, you can never get true airspeed. So B true is square root of 2 times delta P. Whatever the pirostatic group determine the delta P divided by true density. True. The problem is you can never determine true density. So you can never get true airspeed. So this is just essentially theoretical. Okay? So in reality, every single airplane does is indicated airspeed. Or sometimes called equivalent airspeed. It's the same meaning, it's just a slightly different usage. One is for airplane pilots, the other one is airplane designer or engineer. So indicated airspeed BI or equivalent airspeed BE, it's essentially the same thing, is equal to square root of 2 times delta P divided by rho of reference. So this is the value you are going to give as a reference value, reference density. For calibration. Okay? So let's go back once again to the program statement. Okay. So the program statement says you are going to set standard sea level air density as a reference value for calibration. But you are actually flying 20,000 feet. Okay? So here's a problem, okay? Your airplane is believing that you are flying at the sea level because that's what you told the airplane. So based on that information, your airplane shows you are flying 220 knots right now. But the problem is you're actually flying 20,000 feet, not the sea level. Is this accurate? No way. So what is the actual airspeed you're flying if it's 20,000 feet and the 20,000 feet standard density condition? Let's find out. Okay. So airplane is indicating right now, okay? Indicating 220 knots. That's what the program says. Your airplane keeps telling you you are flying with 220 knots based on density sea level. If the density right now is sea level density, you will be flying 220 knots. That's what your airplane is telling you. This is called indicated airspeed. The I is 220 knots. Row reference is row sea level, which we pick up the value here. Sea level value is 2.377 times 10 to the minus 3 slugs per cubic foot. This is only an indicated airspeed, BI. This is not the true airspeed. So imagine yourself, today is a very typical day. If you are actually flying at 20,000 feet. If you are actually flying at the 20,000 feet, and then today happened to be a very standard day, row true. So true density at the 20,000 feet was a very standard value of 1.267 times 10 to minus 3 slugs per cubic foot. Okay. So this is a true density. The problem is you can never measure true density. So you can never get it in reality. But let's assume that this is the density you are flying right now, 20,000 feet. If so, what is the true airspeed? V true. How do you get that? Well, you need to correct the density difference, okay? So V true is whatever the indicated airspeed, 220 knots right now, based on the wrong reference value of density. It's essentially cross square root of density ratio. Okay, so you need to correct it. So 220 knots square root of reference value, which is 2.377 times 10 to the minus 3 slugs per cubic foot, 1.267 times 10 to the minus 3 slugs per cubic foot. I'm taking ratio, so I'm just not going to put the units in. This is the wrong reference. This is the correct true density. So based off of that, you are actually flying 301.33 knots. This is actually what you're flying with. But your airplane keeps telling you you are right now flying 220 knots, you are flying with 220 knots, your airplane keeps telling you, even though you are actually flying with this speed. What's the problem? Problem is wrong reference value. The problem is this density rho can never be measured. Okay, so the only thing you can do is you can tell airplane this is my reference value of density. So based on that reference value of density, you determine the airspeed. And if you give very, very long value, you get the very wrong value of airspeed. Even though you are flying with this speed, your airplane is telling you, hey, right now you're flying with this. Okay? So this is a big difference between indicated airspeed versus true airspeed. Now obviously, if you put the proper reference value, suppose if you're flying 20,000 feet altitude and you're giving very close to the actual value here as a reference, this is going to be very, very close to that. So you can minimize obviously the percent error of your indicated airspeed. But always true that you can never get the true airspeed. This is something you can never have. This is only theoretically possible, academically. You can only have this. This could be very, very close to that, but still indicated airspeed is indicated airspeed. So your airplane's airspeed is always the estimate based on the reference value of density. Okay? So that's the very, very bottom line of this airspeed. That's it.